So last week we proved the product formula of determinant function. Okay, so now let's look at an example. All right, so observing examples of elementary matrices. Okay, the first type is corresponding to replacement row operations. So, for example, okay, we add a multiple of the first row to the second row. All right, so that this is actually doing the for 5 by 5 matrices. This is just doing that alpha. Okay, so we have an alpha here. Because we multiply the first row by alpha and add it to the second row here. But when we look at the transpose of this elementary matrix, look at the transpose, we find that actually the alpha where it goes to this position here. Okay, so it goes to here, and we find that this is actually another elementary matrix corresponding to a different replacement row operation. This time, we actually multiply the second row by alpha and add it to the first row. But anyway, the point is that the transpose of this elementary matrix is another elementary matrix. So by axiom number 2, the determinant of E for alpha, which is equal to 1, right? Because this will be the same as the so this is the okay. And this is 1, and also the determinant of this replacement, this elementary row. Elementary matrix is corresponding to replacement row operation. Is also has determinant equal to 1 by axiom number 2. So this is about replacement. Okay. How about elementary row operator? So second one. For x2 beta, okay. So we multiply the second row by beta. Okay. So it is a diagonal matrix too, right? And its transpose would be the same. As x2 beta, so that the determinant of s2 beta, okay, is equal to beta is equal to determinant of S2 beta transpose. I'm sorry, I want to keep the transpose. Okay. Yeah. Right. And this is by axiom number 3. Okay. The third one, P. So the swap. So this elementary matrix corresponding to swapping the second and the fourth row. Okay, and it's a transpose. When you look at its transpose, you can see this matrix is already a symmetric matrix, so the transpose would be the same. So this is P24. Okay, and so the determinant of P24, which is -1, is determinant of P24 transpose. All right, and this is by, so when you swap the row, so this is by theorem, so exchange 4.1.1. Okay. All right, so you have that. And from the observation, so we summarize. The above finding okay. So the lemma point B, that for elementary matrices, we have an EIJ alpha transpose. Okay, so the transpose of this elementary matrix is actually EJI alpha. Okay, so you just exchange the I and the J. And XI beta transpose is equal to the same because it's symmetric, and the PIJ transpose is equal to PIJ2. Right? So we have this result. And then by taking the determinant, we found that EIJ alpha transpose is equal to the determinant of EIJ alpha. Okay, so the determinant of the transpose of EIJ alpha will be the same as the determinant of EIJ alpha, and also determinant of SI beta transpose is equal to the determinant of XI beta. Okay, so they will not change the value, and the determinant of PIJ transpose is equal to the determinant of PIJ. Okay, so we have this lemma here. All right, so the lemma tells us that for elementary matrices, when you take the transpose of elementary matrices, you will not change their determinant values. Okay, And the following theorem extend the result to arbitrary n by n matrices. All right. So for any n times n matrix A, the determinant of A transpose is equal to the determinant of A. Okay. Okay. Right. So we need to prove this extension because that is true already because this is simple, right? It's true for elementary matrices, but we have to extend to arbitrary matrices. All right, so we note that A is invertible if and only if A transpose is invertible. Okay, by the invertible matrix theorem. Okay, so this is the first things we have to know, right? And now there are two cases to consider. First one is that A is not invertible. Okay. When A is not invertible, then A transpose is also not invertible. So that the determinant of A transpose is 0 because we have proved already that if a matrix is not invertible, then its determinant is 0. Okay. All right, so it's easy. Case number 2, A is invertible. Okay, so the reduced row echelon form of A is the identity matrix. Again, by the invertible matrix theorem. Okay. So there exists a sequence, right? E1, E2, up to Ek of elementary matrices. Okay, such that A can be reduced to the identity matrix. So that would be A here. Okay, this is from chapter 1. Okay. So A inverse. So you can see that so A is, so we know A is invertible, so we know from here we know the, so this product becomes to left inverse of A. So this left inverse must be the inverse of A. Okay, so A inverse would be Okay, and we know this is E1 inverse. Okay. Right, so A inverse. Oh, I'm sorry. Oh, sorry. Okay, so I don't A itself. I'm sorry. So that A is equal to okay. So I'm sorry. So that's A is equal to the inverse of this product. I'm sorry. Yeah, I'm sorry about that. Okay, because A is the right inverse of this product, so that A should be the inverse of that, and this is E1 inverse. All right, and we let Fk defined to be the EI inverse, right? Which is an elementary matrix for all. Okay, right? So in chapter 1, we know the inverse of an elementary matrix is also an elementary matrix. Okay, so we call it as Fi. Okay, and this is from lemma 1.2.b. Right, in chapter 1. All right, so now the transpose of A becomes to F1, Fk minus 1, Fk to transpose. All right, and we know this is Fk transpose, Fk minus 1 transpose, and F1 transpose. Okay. Right, so by repeatedly applying, we put that before, theorem 3.5 there. Okay. All right, so so the determinant of A transpose by the product Fk T, determinant of Fk minus 1 T, determinant of T by theorem 4.2.b. Okay. Oh, no. By repeatedly applying theorem, the product formula 4.2.2. Okay. So when we apply the product formula several times, then the determinant of A transpose becomes to the product of the determinant of each vectors. Yeah. Any questions up here? Okay, and now we will use the lemma 4.21b because that lemma 4.21b tells us that for elementary matrices, that the transpose of an elementary matrix has the same determinant as its original determinant value. So this is the determinant of fk, and this is determinant of fk minus 1, and then this is the determinant of f1. So by lemma, right? So by previous lemma, we can write it down like this one. Okay. And because they are scalars, right? So you can change the order of multiplication. Okay, so we change the order of multiplication because they are scalars. And apply the product formula again. This determinant actually is the determinant of the product of matrices. Okay, so by theorem, by product formula, 4.2.2 again. Okay, and what is this? This is the product of these matrices is A already, and then we have done. Okay. Okay, so with the help of this special case for elementary matrices, and the property of product formula, okay, and also our knowledge about elementary matrices, then so we can prove that this is true. Okay, so the extension is valid to all n times n matrices. Any questions? Okay. Now, this theorem has useful implication. Okay, so I would like to make a remark here. And we will use that quite often. So the rows of A transpose are the columns of A. Right? So this is the first observation. So the rows of the transpose of A are just columns of A. So that all properties of a determinant function goes to R or C have a version for columns. Okay, because when we manipulate the rows of A transpose, okay, for example, if we have two equal rows in A transpose, then the determinant of A transpose is 0, right? But if A transpose has two equal rows, then A has two equal columns. Okay, so that implies that because the A transpose and A has the same determinant, so the determinant of A is also 0 too. So if you have two equal columns, then this matrix has determinant 0. If a row of A transpose is 0 rows, okay, then A has a 0 column. When A transpose has a 0 row, its determinant is 0. So that means that if A has a 0 column, then its determinant is 0 too. Right? So every property of determinant function have version for columns. Now go to axiom number 2. If you do the row replacement on A transpose, this is the same as you do the column replacement on A. Right? You do the replacement. We call it column replacement. It means that you multiply a column of A, add to another column of A. That is called a column operation. So you have replacement row operation corresponding to replacement column operations. But replacement row operations does not change the determinants of A transpose. So that because A transpose has the same determinant as the A, so that if you do the replacement column operations, then the determinant of A does not change. Then the determinant value will not change too. Okay, this is for axiom number 2. For axiom number 3, if you have a row multiplied by a constant alpha, then the determinant will be multiplied by alpha too. Okay, but if you multiply a row in A transpose, it's the same as if you multiply a column of A by alpha. Okay, so when you multiply a column of A by alpha, then the determinant value will be multiplied by alpha too. Okay, so this is the saying that all properties of the determinant functions have a version for columns. Okay, and similarly for linearities. Okay, so I will not. So that I will say it. Determinant of A is linear on any column of A. All right, so that would be useful. And also for swapping two columns of A, we'll change the sign of the determinant value. Okay, so when you swap, because when you swap the two columns of A, it's the same as you swap two rows of A transpose. But swapping introduces sign change. Okay, so that's why when you swap in two columns of A, you will change the sign of the determinant value. And so when scaling, which I have said already, so when you when scaling a column of A by a scalar, alpha, the determinant value will be multiplied by alpha. Okay, the same. All right, so last one about replacement, when adding a multiple of a column of A. So when adding a multiple of a column of A to another column of A, the determinant value will not change. Okay. All right. Now we consider a special case, put as a lemma. So for n-1 times n-1 elementary matrix, this is a common strategy, right? Every time when you want to dig out a property about a general matrix, well, you look at the elementary matrix first, right? Because they are simple matrices. All right, so for m times n elementary matrices, say Eij alpha, Xi beta, and Pij, okay, where alpha, beta are scalars, right, with beta not equal to 0. So we have the determinant right. So we use the n-1 times n-1 elementary matrix. For example, for this elementary matrices, we build an n times n matrix. So this is n times n matrix. And so the first column, except the first one, we have all zeros entries here. For the first row, except the first one, the other entries are all zeros. Okay? And here we have n-1 times n-1 elementary matrices. Okay? When we look at this one, we find that this actually has the same determinant as Eij alpha. Okay? So even though when we extend the elementary matrix into this one, actually this matrix is also elementary. Okay? Also elementary, and so they have, because the determinant is equal to 1. I will say that later on. And the determinant of the same thing we got same. And finally, before I go through the proof, I would like you to understand this determinant function is different from this determinant function. Why? This is a determinant function on what? N by n matrices. But this one is a determinant function on n-1 times n-1 matrices. So they are different functions. Okay. And the lemma is good. It's valid for any determinant functions on m times n matrix, and for any determinant functions on n-1 times n-1 matrices. Okay, so because we haven't proved yet that the existence and uniqueness of determinant function, we haven't yet, right? We only prove that for 2 by 2 matrices, we have one and only one determinant functions. But for general n, we haven't done that yet. Haven't yet. But so up to now, we just saying that if we have one, then we have something, right? So that the premises is that the existence of a determinant function on n by n matrices. But this lemma corresponding to different determinant function, all right? One for n times n matrix, the other for n minus 1 times n minus 1 matrices. Okay? So in this point of view, it is not trivial. Okay, so no matter which determinant function on n times n matrix you check, no matter which determinant function on n minus 1 times n minus 1 matrix you choose, they must be equal here. If you construct the matrices corresponding to here, like you're using n minus 1 times n minus 1 elementary matrices, you will see that they are equal. Okay. And so the proof here is here that so we'll note that. So the important thing is to note that okay, this is 3 types of matrices are n times n elementary matrices. Okay, of the same type. As EIJ and SI beta and the PIJ, respectively. Okay, so this matrix is an elementary matrix corresponding to replacement operations. Okay, so if this one corresponding to so what is it? So what is this exactly? It's elementary, right? So what is that? This is actually E, I plus 1, J plus 1, alpha. Because the ith row in this matrix becomes to the I plus 1 row of this big matrix by this extension. Is that clear? And how about this one? This is the same type, so what is that? Which row has been multiplied by a scalar beta? Which row? In this bigger matrix is the I plus 1 row. Okay. How about this one? This becomes to I plus 1 and J plus 1. Okay. Okay, so they have the same type. EIJ go to EIJ. Okay, so that is the situation. All right, so by theorem, 4 times 1 times G, the last theorem in section 4.1, we have the determinant of this bigger matrix is equal to 1. Okay? And this is 1 for this determinant function. This determinant function is on the n times n matrices. But for determinant function on n minus 1 times n minus 1 matrix, the determinant value is also 1. So they are equal because they are all equal to 1. How about the scaling? The scaling, which is beta, okay, the value is equal to beta, and the same as the determinant of Si beta. Okay, so they are equal because they have the same value beta. The last one, determinant Pij, the value is minus 1. Okay, and so this is Pij, and we have done. Okay, so that is the equality is because from our axioms and all the theorems we proved before. Okay, so they are equal. The extension. Okay, so with this in mind, now we have an extension. Okay, so if we have a matrix constructed by an n minus 1 times n minus 1 matrix M, we have determinant A is equal to the determinant of M. Again, these two determinant functions are different, even though we use the same notation, okay, for our convenience, but they are different, okay? They are different. All right. So the proof that, so note that M is invertible if and only if A is invertible. With the inverse, so we have to provide an inverse, right? So the inverse of A is equal to the inverse of M. It's simple, just multiply this matrix with that matrix, you will see that it's equal to the identity matrix. Okay? So this is very simple to justify. Just do the multiplication. Okay? Just do the multiplication. So that we have two cases to consider. All right? M is not invertible. Okay? Then A is not invertible too. So that determinant of A is equal to 0 is equal to determinant of M. Okay, so the first case is easy. Right. Now the second case, M is invertible. Okay, so again, by the invertible matrix theorem, then M minus 1, the identity matrix, this M minus 1 dimensional identity matrix is the reduced row echelon form of A. I'm sorry, M. And so there exists a sequence E1, E2 up to EK of M minus 1 times M minus 1 elementary matrices okay, such that we have the reduction okay, so we have that. Again, since M is invertible, A is invertible, okay? Right? So since A is also invertible, oh, right? Since A is also invertible, the n times n identity matrix, which can be written in this way, okay, by using the m minus 1 times m minus 1 identity matrix. I write this identity matrix into this form purposely, okay? And so this one is the reduced row echelon form of A, okay? All right, and as we see, A is, by our construct is this way. So can be, right? So can be obtained by applying a corresponding sequence of elementary matrices on A, and this elementary matrices will be so that you can see this identity matrix. It's EK. Right, so A matrix can be reduced to the identity matrix by a corresponding elementary row operations or elementary matrices. And you can see that this elementary matrices are constructed by using the elementary matrices of n times n minus 1 times n minus 1 dimension. Okay, you just do the multiplication. You will see that. Okay, and by lemma 4.2.c, we have the determinant of 1, 0t ei, which is determinant of ei. Okay, for all I. Okay. Right, which we just proved. Oops. Okay, so So by the product formula, again, we use the product formula in Theorem 2.2.2. So we have 1 is equal to the determinant of okay, according to this identity. So this is the determinant of EK, E2, E1, the M. So this is the determinant of EK, the determinant of E2, determinant of E1, and the determinant of M. And by this formula, 1 is equal to determinant of n times n. So this is the determinant of A here. Okay, this is A. Okay, and so it's equal to this is equal to by the product formula. So this is determinant of EK. Determinant of E2, determinant of E1, and determinant of A. All right, so this is 1, this is 2. All right, and so we take 1, divided by 2. All right. So the left-hand side is 1 divided by 1. But the right-hand side, the right-hand side we have determinant of E, okay, determinant of E2, determinant of E1, and determinant of M. Okay, and the denominator is also determinant of EK, because this determinant is equal to determinant of EI. So this is EK, the determinant of E2, and determinant of A here. All right, and so we cancel. Because all these determinants are non-zeros. The determinant value of an elementary matrix is either 1, our constant beta not equal to 0, or -1. Okay, so that you can cancel them. So this implies that the determinant of A is equal to determinant of M, and we have done. Okay, so this is the end of proof here. Okay, so let's take a break of 5 minutes. So please return 11:15. Okay. Now we will give the reason why we need to consider such special cases like this one. But I want to emphasize again that these two determinant functions are different. Okay, so this one is a determinant function on n times n matrices. But this one is a determinant function on n-1 times n-1 matrices. Okay, so they are different functions on different size of matrices. Okay, but they must be equal. That is amazing. Okay, so it's non-trivial. All right. Okay, so now suppose we have a matrix, a big matrix, which is n times n. All right, so we have the ith row and the jth column. Okay, we look at the ith row and the jth column, and now we just remove them. Remove the ith row, remove the jth column. We will reduce the size of A by 1, right? This is quite different from this one. This one is that we insert the M into here so that we extend this matrix. This M is n times n minus 1 times n minus 1. So the dimension of the matrix M is n minus 1. And when we extend it into an n times 1 matrix, okay, by using this construction, this structure. Okay, and so this is the other way. So by removing or by deleting, that's fine. The ith row and the jth column of A, right? So we do this one. We obtain an m minus 1 times m minus 1 matrix. And so we will have, and we call it as Mij. Okay, so the subscript ij means that the first I means we delete the ith row. The second index j means we delete the jth column. And this operation is on A, okay? Which is an m minus 1 times m minus 1 matrix. Okay, so you can look at Mij as an operator. So what is M? You can think about Mij. It's a function. It's a function, right? It's a function from n times n matrix go to m minus 1 times m minus 1 matrix. Is that okay? So it's a function. It's a function. Any questions? So this is the reverse, okay? Reverse from to the previous theorem. All right. So I want to prove a an important formula. Right? I'm sorry. Because this is the sequence number of the theorem in the textbook. I don't want to change it. Even though the logical sequence for me should be in this position. Right? Okay, so, but this is called a cofactor expansion. I will explain what is a cofactor using rho I. Okay, so let A be an n times n matrix. Okay, and here A we call A11, A12, A1n, AI1, AI2, AIN, AN1, AN2, ANN. And so we used Ri to indicate the ith row of the matrix A. Okay, so just the convention. All right, so then the determinant of A. Okay, the determinant of A can be computed in the following way. All right, so you can do the following way. Expansion using rho I means that we were using rho I. So this is rho I here. All right, so this is Ij, right? I1, I2, I3 up to In. Okay, so the Aij is the component in the ith row. Then multiply with sign, which is -1 to the I plus j's power. And a determinant of n-1 times n-1 matrix. What is this matrix? Well, this matrix is obtained by removing the ith row of A and the jth column of A. Right? So again, this is a determinant function. On n times n matrices. Right? Arbitrary determinant function. And again, this is a determinant function. On n-1 times n-1 matrices. Okay. So they are different functions. They are different functions. But we can establish the identity. Yeah. So it's called expansion using rho I. Okay. So Aij is AI1, AI2 up to AIN. They are entries of the ith row. Okay. And this n-1 dimensional matrix is obtained by removing the ith row and then removing the jth column corresponding to Aij. Okay. So once we've done that, this matrix is n-1 times n-1 matrices. Okay? Any questions about the expression? And what is cofactor? Okay. Cofactor means that co-Aij. So this quantity Okay. So this quantity defined to be Cij A Oh, I think okay. Okay, later on I will say a mistake. Anyway, so this is including the sign, which is called the cofactor of Aij. Okay, because in this expansion formula, it will coexist with the Aij. Okay, and the cofactor of Aij is defined to be this scalar, this quantity. Okay. Okay, so now I'll give a proof for the cofactor expansion using rho I. Now, the I0 here, we know the I0 is AI1, AI2 up to AIN, right? So it can be expressed as a linear combination of standard unit vector so this is a summation j from 1 to n, Aij and Ej. Okay, so Ej is our standard unit vectors. Okay. Okay, so now the determinant of A becomes to the determinant of so we have R1 summation j from 1 to n and A Ij and Ej Rn. Okay, so the Ri is represented by a linear combination of the standard unit row vector Ej. Okay, so by linearity on any row, this becomes to summation j from 1 to n and the Aij determinant of R1 Ej Rn. Okay, here Ej is in the ith row. Okay, and we will use a notation to simplify the expression. This matrix will be called Ai and Ej. Okay, so what is Ei? Ai Ej, right? So this is defined to be this one. 1 dot 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 EJ Rn. This is ith row. Okay, so that this is a matrix. Okay, from A by replacing the ith row of A with EJ. Okay, with EJ. So the ith row has been replaced. The ith row of A has been replaced by the row vector EJ, the standard unit row vector. Okay. So this is the expansion. This is from the linearity in any row. Okay, so now look at AI EJ. What is AI EJ? Well, it's right, so this is the jth column. And here again, this is the ith row. Right? Because we replace the ith row of A by EJ. And the EJ has entry 1 in the jth column here. Now we can use replacement row operation to cancel, to eliminate all the entries above and below this one. Okay, so we can go to record Bij A11 by replacement row operations. Okay, so by replacement operation, we can eliminate, right? Forward elimination, backward elimination, right? We eliminate all the non-zero entries above and below these entries. Is that okay? And this matrix we'll call Bij. So what is Bij? Bij can be formed from matrix A, all right? So that first you turn the ith row and the jth column to be all zeros, and then change the ij entry to 1. Okay, so in the ith row there is only one non-zero entry, 1 here. All entries are all zeros. In the jth column, we have 1 in the ith component. All entries are zeros. Okay? So that is the... All right, so this is the ith row. And this is the jth column. And when we're doing these operations, we will not change the value of the determinant. So that determinant of AI, EJ, will equal to the determinant of Bij. So these two matrices has the same determinant. Now, we will move this ij entry, this one, goes to here. So the one in here is in the ij position. But we want to move this one to the 1, 1 position. How to do that? Row operation and column operation. Row exchange, right? So you can do a row exchange, move up here, and do the column exchange to there, right? But doing the row exchange, every time you change the sign, and doing the column exchange, you also change the sign, right? So that they will goes to what? Goes to this matrix. Right? So by I minus 1 row exchange and up to here, right? And then by j minus 1 column exchanges. All right? So you move this row up by I minus 1 row exchanges. And you move this column to the left by j minus 1 column exchanges. And you end up with this matrix. What is in this matrix? 1 is go there, right? And all 0 here. So the rest will be what? Will be the mij operator on the matrix A. So that means that it's equivalent to removing or deleting the ith row and the just column of A, which is just Mij, right? We consider before here, Mij there. All right, and so doing so, we should change the sign of the determinant of B, so that how many signs we have to change? I minus 1 plus j plus 1 determinant of so determinant right? But this is equal to determinant of Mij A by theorem 4.2. A. Okay, we just proved that. But this vector, because minus 1 minus 1, so this is equal to I plus j. Same. All right, so when we combine so when we do the so now this expansion by using the linearity on the ith row. Okay, so this one begin with this. This is equal to this one, and from here we have this identity. So this implies that determinant of Bij is equal to -1 I plus j, and determinant of Mij A. Okay. Because when you multiply -1 I plus j, you have -1 2i plus 2j. But for even number, when the exponent is an even number, -1 an even number is 1. Okay. Okay, so now the determinant of A becomes to summation j from 1 to n aij, and the -1 I plus j determinant of, and this is what we have. Okay. And we have done. Okay, so, and I find a typo in okay, correction. In my Hangout, my lecture notes, I write this to be okay. I forgot to delete it. Okay, when I copied, so this is actual. Defined to be it's called ij's cofactor of A. All right, so I'm sorry, I forgot to remove this vector. Okay, so it's appeared in my lecture notes, so you have to remove it. I already removed that? Really? Oh. Sorry. Okay, because maybe this one is old one. Maybe I got a new one. Interesting. How come I have two versions? Okay. Anyway, if you got a version, I don't know why, but anyway, if you got a version, just remove this vector. Okay. All right. So this is the Cofactor expansion using rho I. So that as I give the remark, we have one prime. The cofactor expansion using column J. Okay. So again, we let A equal to A11 up to A1j up to A1n, and A21 up to A2j up to A2n, AN1, ANJ, ANN. So I write down it as A1, AJ, AN. Okay, so A consists, it has n columns, n columns here. So this is the jth column. Then the determinant of A, okay, can be expanded I from 1 to n, Aij. Okay, so J fixed, but I changing. So you have 1j, 2j, 3j, except up to nj, and the minus 1 I plus j, and the determinant of same Mij. Okay, so by the definition of the cofactor, so this is Aij and the Cija. Okay, so we have a version, okay, column version there. So we can expand the determinant value according to the jth column. Okay, so we use the entries in the j columns and their cofactors together, okay, to find it. Okay, and the proof was the same, but so I just omitted. Okay. Any questions about the cofactor expansion? All right. Now we need a oh, by the way, I will send you the rest of chapter 4 to you as soon as possible, like, because that okay. All right. The Mij, all right, this operation, the Mij downsize n times M matrix by 1. We need a further downsizing in the proof of uniqueness and existence of determinant function. So, so now A here, you can pick up 2 rows and 2 columns. So you can pick up the ith row and the kth row. You can pick up the jth column and the lth column, right? And you turn them to deleting the ith, kth row and the jth, lth column of A. Now give us a matrix called IKJLA. Okay. And n minus 2 times n minus 2 matrix. Okay, so we delete 2 rows and 2 columns of the original matrix A, and what we obtain is an n minus 2 times n minus 2 matrix. So that the MIKJL is an operator from goes to matrix. Okay? So now we need the following result. 4-term, 2-term B is called expansion using 2 rows. Okay. All right. So let Aij be an n times n matrix. Then, for any I, k, and I purposely, for simplicity, that because we just picked 2 rows, so I want the index I is less than index k. Okay, so I is upper, and k is lower. So for any ik in between 1 and 0, 1 and n, so we have the following expansion. Determinant of A can be written okay, and column J and column L. In here, the column index J here is less than column index L. And -1, okay, I plus k plus j plus L. Okay, so involve every index. Okay, not surprise. Okay, but the surprising thing is Aij akl minus ail and the akj times the determinants of m ik jl a. Okay. So when we downsize the matrix A by 2 steps, by 2, okay, so we can use the determinant functions on n-2 times n-2 matrices. Okay, and the formula becomes to like this one. Okay, so here the entries has been used is the I0 and the K0. Okay, and the JL minus KL here. Okay. And for that, the J and the L, they should be J is smaller than the L index. Okay, so to have this difference. Okay, so the proof is quite similar to the proof for expansion using a row, or expansion using column. But here, let me, so the I0, because we are using 2 rows, I0 and the K0. So the I0 will be expressed by linear combination of standard unit row vector AIN and K is AK1 E1 plus AK2 E2 plus AKN EN. Okay. All right, so by the linearity on any row, right? We have that the determinant A, the determinant of so this is R1 and the summation J from 1 to N Aij Ej. And the case row, I use L, 1 to N, AKL, EL, N, So this is the K0, the I0, and this is the K0. All right, so the I0 is a linear combination of standard unit row vectors, and the K0 is also a linear combination of the standard unit vectors. Okay, so by linearity, so now we have a double sum, right? So we have j from 1 to n, L from 1 to n, and we have aij, we have akl, and the determinant of R1, ej, el, and Rn. Okay? And here, this is the I0. Here is the K0. Okay, and for the okay, I will define A, I, K, E, J, E, L. Okay. So where A, I, K, E, J, E, L is defined to be this matrix. Okay. So that is it's R1, EJ, EL, En. Okay. This is the I0. This is L0, K0. Okay, so this is an n times n matrix obtained from A by replacing the i's row and the k's row of A, okay, by with E, J, and EL respectively. Okay. Now, if we replace the i's row and k's row by same element, same standard unit vector, so if now, since A determinant of A, I, K, E, J, E, L, it's 0 if J equal to L. By theorem, the equal rho 4.1.8. Okay, so if we replace, so if J equal to L means these two rows are equal. If these two rows are equal, then the determinant is 0, right? So if J and L they are the same. All right, so we can eliminate the possibility for I and J equal. Right? So that the determinant of A can becomes to 1 less than J So let J is less than L. And the first one is Aij, AKL of determinant of A, IK, and E, J, EL. The first one. The other is AIL and AKJ, right? So, and the determinant of A, IK, and the EL, EJ. Okay, right? Right. So here, we must have J not equal to L. But J not equal to L has two possibilities. Either J is bigger than L or J is less than L. Okay. So I just keep that J is less than L. So this one is the first part. The other is opposite. I use IL and KJ. Here is IJ, KL. So J is less than L. But here, L is greater than J. Right? So the sum become to this sum. Okay? Become to this sum. All right, so that we have to look at here. Now the Aij, Aik of Ej, El. So look at that. So this is A. I'm sorry. And A1 J, A1 L, A1 N. And here we assume J is less than L, right? So J appear first, then K, then L, I'm sorry, right? And the 0, 1, 0, 0. And so the ith row, I is upper than the kth row. So this is the kth row. Okay? So we have KL entries here, IJ entries here, and this is A, N1, A, NJ, A, NL, A, NN. Okay? Now we have this one and this one. So we can use the replacement operation to eliminate all the entries above, okay, above and below this one, okay? And also, you can use this one to eliminate all the entries above or below it. So that this is becomes true. We call B, IJ, and KL. Right, so this matrix is very interesting. This is 0, 0, A, 1, N, 0, 1, 0, 0, 0, 0, 1, 0, A, N, 1, A, and J, A, and L, A, and N. Okay. So here, this is the J's column. This is the L's column. Here is the ith row. Here is the kth row. Okay? So that we have moving of the things. So our purpose, again, for this one, I want to move it to here, to the 1, 1 position. And then I want to move this one to the 2, 2 position here. Okay? So moving. Now, for this one, how many row exchanges do we need? It's I minus 1. Okay? And so I minus 1 row exchanges and the j minus 1 column exchanges there. Okay? And similarly, for this one to go to here, now because that I will just want to move to the second row, so I need k minus 2 row exchanges and L minus 2 column exchanges. Okay, so down to here, I will have so the way it's 1 and 1. Okay, so this one is moving by this go to there, this go there, and the rest becomes 2m and I, k, j, l, a goes to here, right? So that so we were by I minus 1 plus k minus 2 row operations, row exchanges, and this to move on the and j minus 1 plus L minus 2 column exchanges. Okay. And you can see that because so k minus 2 is still non-negative. This is the reason why we need the order I is less than k, and also we have to know that L is at least 2, so that L minus 2 is also non-negative. So we are able to do so. Okay, so this is the same thing. All right, so from that, so we know in here, this is by replacement row operations. Okay, so we know that the determinant of A, I, K, E, J, E, L is equal to the determinant of this matrix B, I, J, and the K, L. Right? And to do this one, we need all these exchanges. So the sign we need to change is minus 1. So it will be M minus 1 plus K minus 1 plus J minus 2. Oh, K minus 2, J minus 1, and L minus 2. All right, and the determinant. So again, that the determinant of this matrix is the same as determinant of this matrix and the same as determinant of this matrix. Right? So we apply the two times. So we apply the theorem 4.2.8 two times, and then we get to here. Okay, and the 1, 2, 1, 2 is 6. So this is the same as I plus k plus j plus l. Okay, so we get this one. All right, and so that we turn at least that so we are able to turn this one, okay, to the theorem is here, okay, to here, because we have that. So the same here. But the other one, this one, we have minus sign. So what is the reason why we have minus sign here? Okay, and I think I have already stored your time for about 15 minutes, so I have to stop here. Okay, so I will explain next week that why we have to introduce the minus sign. Okay, for the rest of part, for this part. Okay, because AIL, AKJ, right? AIL, AKJ, but we have to put a minus sign here when we turn this one back to there. And the key reason is because L is bigger than J. Okay? I'll explain that next week. Okay, so I'll stop here.